Hello, it's Keith here, and this is lesson 7 of the YQuest series of 68,000 assembly programming tutorials. Today we're going to be looking at the Atari ST version of the game. I've got it just over there, you can kind of see it. And if I just use my joypad here, we can play the game. Now, there is a limitation of this version, and you can see when we move horizontally, the movement's quite jerky. We're moving in sort of 8 pixel wide blocks, and that's because the way the bit planes are aligned in this system, basically 8 pixels are in a single byte. So it's very easy for us to move vertically by 1 pixel, but it's a bit tricky for us to move horizontally by a single pixel. So today's version is going to have that limitation. We're going to look over the code of this today. This is based on the simple series, the previous tutorial I did of just moving a smiley around the screen. So it was extended to be this version. And then in a future episode, we're going to learn how to modify the sprite code and make it so that we have much nicer smooth movement. But today we're going to go over what we've got for this version, which I still think is pretty good. It's a nice fun little game, and I was able to port it to this system pretty quickly. So let's go over to the source code and let's see what we got. Okay, so here is the Atari ST version of the game. Now, because of that horizontal movement limitation, we're basically locking down the calculations for the collision detection so that the calculations are being done at the same resolution that things are shown. If internally it thought two objects were slightly overlapping, but visually they weren't being shown like that because of the 8 pixel separation, it would make you die for no apparent reason. So to avoid that, we're reducing the resolution of the collision detection within the common code here. We're then defining the size of the screen. Each of the systems has a different screen size, so we always need to make sure that the code is programmed according to the screen resolution of the actual system. We've then got some code here that's setting up the screen. Now, we've just discussed this before in the simple series, but basically we're switching into supervisor mode, and then we're defining a 320 by 200 screen here, and we're defining the screen memory just down here. Now, the screen memory is slightly larger than it needs to be. The screen's 320 by 200, I think it is. But we're actually defining more memory than that, and that's because we need to be 256 byte aligned. So we define a slightly larger area than that, and then we sort of clear the top bit down so that we know that we've got a 256 byte boundary there. Now, that's defining the screen. What we're doing next is we're defining the palette here. The palette is in native format all the way down the bottom here. This is the format that the Atari ST is expecting, I believe. So we're initializing that, and then we're initializing our joystick handler. Let's have a word about that joystick handler again. It was in the simple series, so it's nothing we've not seen before, but basically what we have is we have to install a joystick handler into the operating system, interrupt handlers. When a button on the joystick is pressed, a directional or fire button, we are running this joystick handler, and that is transferring both joysticks data to a buffer, which you can see just here. So that's turning on that using the operating system traps here. So that will get us our joystick, and once we've done that, we can then read these addresses to see the joystick settings. Very good. Now, once we've got our joystick handler and our graphics set up, what we're doing here is we're clearing the game memory, the user RAM. You can see down here, this is all of the variables the game has within it, all of the positions of the objects, the enemies, the remaining crystals for the level, everything like that. Here's the start of the new game routine, also the first game, of course. We're setting our lives back to 3, zeroing our score, zeroing our level, resetting the player's sprite back to 0, stopping any sound and clearing the screen. And then we show the title picture to the screen. We've got that amazing title picture. Well, I think it's amazing even if the rest of the world disagrees with me. Here it is. So that's the title picture. So 1 byte per tile. Basically we're using the game sprites to draw that graphic. It's a nice easy way of making a graphic. So get sprite address will calculate the memory address of the source data. The memory data of the sprite is all just here. So we're calculating an address within this area for the sprite that we want to show onto the screen, and show sprite will actually do the job of transferring the data to the screen. Show sprite is pretty much the same as the old simple series version. We're repeating that until we've drawn all the tiles. We're then showing some text onto the screen. We've got a bitmap font that again is the same format as the sprites, so it's all been done by that sprite code. We'll see that later on. Here's the start level. We wait for fire button to be pressed to clear the screen, reset the player, center the player, give the player some invincibility, that kind of thing, and initialize the contents of the level. This actually runs every level, not just the first level. We've then got the control loop here. Read control joules will read in from the joystick in this case. So you can see it's just reading in there, and it's converting it to the correct format for these tutorials, which is up, down, left, right, and then fire. So we're just shifting some bits around there to get things in the format that we want. So this routine here is a delay, and it also just reads in any joystick presses and stores them in D2 for processing later. What we do next is we then draw the user interface, that's the score and the remaining crystals and things in the corners, and we remove the player sprite from the screen with the blank sprite routine. Blank sprite uses A4 to point to an object. Now in this game, basically every object has an 8-byte definition, and that defines the sprite that's being shown with it, the X and Y position, and then some movement attributes, things like that. So we're using that to take that object off the screen, and we'll see that routine later. We then have a key timeout. The game works by acceleration, so if I press up and release, then I'll start moving up, and I'll keep moving up until I press down for the same amount of time to stop. What this means though is if I hold up, I will start accelerating, and I could accelerate extremely fast. So to avoid that, we have a key timeout, and if the key timeout is still occurring, we skip over the direction reading. So basically an up press will be ignored for 5 ticks before the next up press is processed, and the acceleration will increase again. The way we change the acceleration is with these pointers to the acceleration X and Y, and if the direction is pressed, then we are just increasing the Y acceleration or the X acceleration, or decreasing it, of course, depending on what direction is being pressed. When fire is being pressed, we're using the multi-platform player fire bullet code here. If the second fire is being pressed, we're actually stopping all movement here. I don't know if this system actually has a second fire, but I don't think it does. It might be a bit unfortunate. Anyway, if we had one, we would stop the movement there. So that's what those routines do. And then we're updating the key timeout, which would be set by the direction keys here, and it's not set by the fire. Our clear screen routine here is very simple. All we're doing is we're getting that memory address of the screen, and we're writing all the bytes back to 0 here. And we're using CLDIO, which is a common clear routine, which just clears D1 bytes from memory address A3 there. That's a simple routine I use. Here's our print character routine. We're using the font data, and we're basically using the show sprite routine here. Now the font has no characters below 32, and each of the bitmaps, the sprites or font, are both the same. They use 32 bytes for each object, so we need to shift to the left 5 times to calculate the sprite number within the font that we want to show, effectively the character. So that's what we do there. Blank sprite uses an A4 object, and it checks the collision program. Now a collision program over 250 is a dead object, so if it's 255 it's never been used. If it's 254 the player's killed it, and it's probably coming back, but not yet. So if it's below 255 we want to clear it, but if it's over 255 it's already gone from the screen, and we don't want to keep clearing it because we'd end up with a area of the screen that was flashing blank, and if anything else went over it would be being cleared, so we skip over that in that case. Get sprite address is very similar to this routine here. Once again, we're multiplying the sprite number we want to show by 32 here, and then we're getting the sprite frame, and we're multiplying that up as well and adding it. Now there's 4 banks of sprites. I can show you them just here. There's 4 blanks just here, and this is for 4 frames of animation, and there's 16 sprites in each. So that is calculating the address according to the selected sprite number and also the current bank, and the bank automatically increments itself between 0 and 3. Here's show sprite. This is for arbitrary sprites. We can show anything we want anywhere we want, and that's used during the title screen, but mostly we use do get sprite object. That gets the sprite number from the A4 object. There's loads of typos in my code. It was ported from the Z80, and so it says IX when it's now A4. So we get the settings from A4, we get the sprite number, the XPOS, the YPOS. You notice we're having to shift down the XPOS because we are only working in byte blocks on this system, and that's 8 pixels, so we're having to shift that down. As I say, we'll fix that later on in another lesson. And then we're transferring the data to the screen. Now the Atari ST screen is a bit weird. I'll go very quickly here, but I covered it in the simple series as well. Basically it works in words. So if you think of a pixel is 4 bits, that's 16 colors. A bit plane is where all of the bit zeros are in one block, and all the bit ones are in one block, and all the bit twos are in one block, and all the bit threes in one block. That's what bit planes are. And in the case of the Atari ST, 2 bytes of bit zeros are together, so 16 pixels worth, and then 16 pixels worth of bit ones, and so on. And that's a pain. It's quite a pain. So we have to check if we're on an odd or an even block boundary for when we're moving across the screen. and it's all quite annoying. So we've got the code there to cope with things, and we're transferring the data to the 4-bit planes here that make up a single 8 pixel wide block here, the 4-bit planes that make up the 16 colors there. So we're transferring those for that line, and then we're cycling to do the next line. Basically though, this will effectively draw the entire sprite, in this case the objects, but the smiley in the previous simple series, and that's what we're using here. And as I say, we're going to see a later version which is much better and a bit more complicated, but it can handle per pixel movement in theory. Get screen pos calculates the memory address within the screen base, and it will work out the position within the screen that we need for an XY coordinate, and so then we can transfer data to that memory address. You can see we're using get screen pos just here to calculate the starting address when we start moving a bit data. Here's our keyboard scanner. We've discussed that briefly. Process 1 is converting it. Wait for fire is a routine that waits for the fire to be pressed down and then released. It's basically used at the end of a level, so that if the player is holding down fire frantically playing, well, we want to show them, you know, you've won the level, and then they realise, they release the fire, and then they press it again, so that you've got a definite pause between the next level, or when the player's died, of course. So that's used there. And then we've discussed these already. We've got some common code here. This is multi-platform stuff. I'm not discussing it here because there's an awful lot of it. I actually discussed it in the Z80 series, and the code has hardly changed. It was I used a script I wrote to port some of the code across. All the labels are the same. The function of all the modules is the same. So if you want to see how all of that works, please see the Z80 series, because as I say, I spent 4 episodes covering that. I don't want to repeat almost the exact same thing again. Finally, we've got our BSS section here. BSS is a set of data that is allocated to us, but is starting at 0. I believe it stands for blocks started by symbol, but it basically means it exists, it's allocated, but it's zeros, so you can't put sprite data in there. Basically, that's all it is. So there we go. That's all we have for today. So as I say, we're going to be coming back to this. So we're going to do a combination episode between the Atari ST and the Amiga, because they both had the same problem of having difficulty moving per pixel level. So we're going to have a improved episode where we see the YQuest2 code, which has that problem fixed. But if you're really impatient and you can't be bothered to wait for that, you can go to the website and download the source code because it's already written. So maybe you want to do that. But whatever you do, say if you like the source code, you go ahead and go to my website and download it. And as I always say, you're welcome to use my source code in any way you can manage to do so. I don't care. You can use it in your own programs. You don't need to give me credit or anything. It's just there for you to enjoy and benefit from. So go ahead and do that. If you've liked the video, I would appreciate it if you like the video. Click the like button, because YouTube recommends my likes, and if you subscribe, it really improves my motivation. And you need to keep the motivation up if you're going to keep making videos. I'm making 6 videos a week at the moment, so obviously it takes a lot of work. But anyway, whatever you do, I wish you all the best with your programming. Hope you have a lot of fun with your Atari ST. Thanks for watching today, and goodbye.